Good afternoon, students. Today we are starting with the second part of revision for the module number 3. Okay. So in this particular revision part, what we are going to see, we are going to see some kind of composite transformations, right? That kind of revision we are going to see again. Some reflections, etc. Reflection, shear transformation. That particular part we are going to see. The purpose of having the revision is that after every module or 2 modules, if you have the revision, then that kind of thing will be the concepts will be concrete in your mind, and you can start working on it. If you are facing any difficulty, we can have the session, we can have discussion, something like that. Okay. So today we are starting with the homogeneous coordinates part. Okay, starting with the homogeneous part, and after that we'll see some of the points related to the how that 2D transformation, when it's come to say a particular point, like say rotation with reference to fixed point, then also rotation, whatever matrix we have got or whatever equation we have got about the rotation is only the rotation with reference to a origin. Similarly, scaling, we have find out the matrix which works well for rotation with reference to a, sorry, the scaling we got is scaling with reference to a origin. So now sometimes it may require that a kind of fixed point may be required, and with reference to that fixed point we may require to do rotation of the object. So during our discussion in detail about this, we have discussed how that particular thing can be achieved by us, right? So same thing we are going to see here one by one. So for that we start with the homogeneous coordinates. Okay, homogeneous coordinate means normally when we write the matrix, we write that 0 1 1. So 2 by 2 kind of matrices we have written, right? So in homogeneous matrices, we try to put the matrices in 3 by 3 kind of matrix format. Okay, for rotation we got cos theta sin theta minus sin theta cos theta. This 2 by 2 kind of matrix we got, right? So instead of that, we try to get the matrix in the form of 3 by 3. So that will be a better option for us. So reason for having such kind of thing is that it will help us to get the things in a much more better way when it comes to work with that particular kind of object and performs a transformation on that. Then whenever we are work in terms of matrix, then it's always a beneficial thing. Okay, so its main intention to have the homogeneous matrix is that to have 3 by 3 matrix. Okay, and when we are working with this particular 3 by 3 homogeneous matrix with the coordinate of the vertex of the given object or endpoint of that line, so it will be very much easier to perform the matrix multiplication, and by that way to get the coordinate value for the vertices or coordinate values for the end point of the given line. Okay, so homogeneous coordinates for the translation, it is 1 0 0 0 1 0 tx ty and 1, where tx and ty represent the translation, right? There are two factors for the translation. Tx stands for translation in x direction, right? And ty gives the translation in the y direction, right? So in this way we can get the tx and ty format for this particular purpose. This way we can get the tx and ty format for, I think the screen is not visible to you. It was added in the stream, but okay, now the screen is visible to you, correct? So what we have discussed, that what is the reason for having the homogeneous coordinates? The reason is that when we are having homogeneous coordinates, that is in terms of 3 by 3 matrix. Okay, so the translation matrix I will get it as 1 0 0 0 1 0 tx ty and 1. Okay, so here what will happen? See, as shown in the diagram in the slide, see x dash y dash 1 is equal to x y 1, this one matrix. This first matrix x y and 1, this particular matrix represent the coordinate value of that particular pixel, right? And the second matrix, that is 1 0 0 0 1 0 and tx ty 1, this represent the translation matrix, right? So when we perform the translation operation on this pixel with coordinate value x comma y comma 1, or the pixel with coordinate value x comma y, right, we'll finally get the value as, see, x into 1, so x, y into 0 is 0, so 1, then 1 into tx is equal to tx. So final, the coordinate value I will get as x plus tx comma y plus ty. So, and see, this one will remain as this. Okay, because for the last row it is x into 0, y into 0, and it's 1 into 1. So the last value remains 1. So the new pixel that we are supposed to put or supposed to display will be at location x plus tx comma y plus ty. Okay, so similarly for rotation, we'll get the 3 by 3 matrix or homogeneous coordinates for rotation will be cos theta sin theta 0, then minus sin theta cos theta 0, then 0 0 1, right? So in this particular format we'll get. So reasons for having this in general is that it will help us to perform the matrix multiplications very much easily when we have to perform such kind of transformations or transformation operations, right? Otherwise, see, it will be very much difficult to see apply or calculate the coordinate values of x and y coordinate values for the pixels separately, right? So that will be time consuming. So always it's better to perform it in terms of the matrix multiplications for a better and faster results. For scaling, I will get sx 0 0, then 0 sy 0 0 0 1 as shown in the screen, and we have discussed this particular pattern much more details, right? So for translation, I can say that it is tx comma ty, something like that. Rotation is normally represented in terms of say the rotation in anti-clockwise direction by the angle theta, right? So that angle theta is in anti-clockwise direction. It's in anti-clockwise direction. What will happen when I require it in clockwise direction? Then Instead of plus theta, mark it as minus theta. Minus theta for clockwise direction of the particular object. Then for scaling, the scaling factors Sx and Sy. These are the two scaling factors, that is scaling in x direction and scaling in the y direction of the particular object. Okay. So after that we'll come to the composite transformations. Composite transformation means uh, it is a sequence of transformations. Okay. The composite transformations means, see, normally perform one operation, like say I perform translation of the object and I stop, right? In composite transformation, what will happen? I have done the translation. After that, I will take the translated object, and on that particular object I will try to do some another operation, like say after translation I just think to do rotation of that object. Okay. Or after translation I want to do scaling of that object, or after first doing translation I will again want to do the translation of that object. So such kind of transformations are called as composite transformations. Means whenever we are performing more than one transformation operation on the given object, it is called as a composite transformation. Okay, we'll see some of the basic examples, like two translations I have done. Uh, See, first I have taken the object and moved here. Then again I have taken the object from that location and moved ahead. Okay. So this is two times translation. So how this composite translation I can work? So instead of doing it two times, I can do that. Whatever is the first translation, so add it with the second translation. So the final value I can mention. As you are able to see on the screen, see this tx final translation value I can get it as tx1 plus ty1 for tx, right? And for ty it will be ty1 plus ty2. See here the row measure method is used. Okay, so that rows are columns are converted in row. So don't get confused with this. So the other way that we are forming, like 1 0 0 0 1 0 and tx ty and 1. So it's same, only row measure or column measure things matters, but thing remains same. If you are doing the same, if you are doing one translation by another translation, then simply add the two translations, you will get the result. Okay, simply add the two translations. I can say that, see, I have one object, I have translated that object by 10 in x direction. Y direction, assume that in y direction I haven't done any translation. In x direction I translated by 10. Again I translated by 30. Okay. So instead of doing it two times, I can translate that object from beginning by 40 units, right? 10 plus 30 is 40. So I can translate it in x direction by 40. So it's very simple to have the two translations, two consecutive translations. Okay. For rotations, if say assume that I have rotated one object by in anti-clockwise direction by 30 degrees. Okay, and the same object I have rotated afterwards by 90 degrees. Sorry, after that I have rotated by 60 degrees. So what I can do, I can add these angles, like 30 plus this 60. I will add this, it comes to 90. So I can take the operation simply by the, take the anti-clockwise rotation by 90 degrees, right? So rotation is done in additive way. Okay, you can add it. Now we come to the scaling part. In scaling, basically what we do, we enlarge the size of object or we reduce the size of object, correct? We either enlarge or we reduce the size of object whenever the scaling vector is greater than 1, then enlargement of the object takes place. When the scaling factor is less than 1, the object will reduce, correct? the object will be reduced. So scaling is done in with help of two scaling factors. Sx means scaling in the x direction. Sy is the scaling in the y direction. Correct? So Sx and Sy, these are the scaling factors. Right? So here scaling of the object is given. How we can perform the two consecutive scalings like Sx to S0 0, then 0 Sy to 0. So this is the second scaling multiplied with the scaling with scaling vectors Sx1 0 0, then 0 Sy1 0, then 0 0 1. Right? When this multiplication is done, matrix multiplication is done, finally what will get the scaling. When we perform two scalings, one scaling followed by another scaling, then it is multiplicative. It is multiplicative. Multiplicative means what? See, initially I have done scaling by 2 and afterwards I have done scaling by 3. Okay. So the total scaling done is 2 into 3. That is 6 times the object is scaled compared to the previous one. Okay, that's why the scaling final scaling matrix here we got it as Sx1 into Sx2 0 0, then 0 Sy1 into Sy2 0, and final row is 0 0 1. Right? So scaling is multiplicative. So see, like say for example I have one square, I scale, just assume that it is scaled in x direction only. So we have scaled in x direction by 2. So its size is double. It will, the square is converted in rectangle now. Correct? Now that particular rectangle we have taken and again scaled it by 3 in again x direction. We are not doing change in the y direction. Okay. So previous size of the original size of the square is 1 unit. Just assume. Then after the when we scale it by 2 in Sx equal to 2, then it will become a rectangle with x value as a unit 2. When we apply again scaling on that by Sx equal to 3, right? So previous size is 2 into 3. That's why it will become a rectangle with unit length in x direction is 6. Correct? So scaling is multiplicative. I remember that I have given you example of, say, you take the Xerox, right? You go to the Xerox person and ask him to do, say, reduction of your particular object. So original size is 100, right? He will reduce it by, say, by putting 0.8 scaling factor, means 80% he will take. You say that they are still it is big. Then after that, instead of taking your original certificate, what will do? He will take the Xerox with 80% reduction, right? He will put there and again apply the reduction in that. So by that way, it will further reduce. So the same concept is used by that particular Xerox person, right? See, sometimes what happen, we require to perform a kind of operation with reference to a fixed point. Here we are going to see the rotation of the object with reference to a fixed point. Rotation of the object with reference to a fixed point. Whatever equation we have seen, whatever matrix we have got for the rotation, okay, so that particular rotation matrix we got is only with reference to origin. Okay, so cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So this particular matrix we got, that particular matrix works with reference to origin. So when I take the triangle and I rotate by, say, 30 degrees in anti-clockwise direction, it is rotated with reference to the origin. Sometimes you may require that it should be rotated with reference to some other point. So here is a diagram. So we have to apply some different mechanism to work with this. Okay, we have to apply with some different kind of mechanism with this, where we have to take help of the translation. Okay, so as shown in this diagram, just assume that this is a triangle given to us. It's a triangle. Say that this is a triangle ABC. We are selected one point on this triangle. We call it as a fixed point or pivot point, and with reference to this point we are going to rotate this particular triangle. Okay, we want to rotate this particular triangle. First step, see, we are having the rotation matrix which actually works with reference to origin. It works with reference to origin. Okay, so that it's necessary for us to take this particular fixed point to origin. Okay, what are the points shown here as xr comma yr? See, this particular point where I have pointed my mouse. Okay, so this particular point first taken to the origin. So which operation we have to use? We have to use the translation. Correct, we have to translate it in minus direction. Suppose this particular fixed point is having coordinate value xf comma yf. Okay, so we have to translate by minus xf and minus yf, right? So this particular point will come to the origin. This particular point will be taken to origin. So as shown in the diagram B, this triangle I got here. Okay, when we say that we are moving that fixed point to the origin, actually we are moving that fixed point and the particular object. Here the object is triangle. Correct, we are moving that triangle in such way that that particular fixed point will coincide with the origin. Okay, so as shown in the diagram B, it is coincide with this particular origin. Now we perform this rotation. Okay, say we can say that it is rotated in clockwise direction by 90 degrees, so that we got the diagram like this as shown in the diagram C. Correct, but this is not what we actually expect. Correct, this is not what we actually expect. Actually, your triangle is to be rotated with reference to this point, and so the diagram should be here only. Correct, but right now you have done rotation, but at this moment the rotated triangle is with some diagram at the bottom. Right, so we are doing reverse translation of this. We are doing reverse translation of this. So see, initially we have taken this fixed point to the origin. Now by the same amount, if I do this reverse translation from this point to this by the same amount, then it will reach here. Correct, so what is done, this particular fixed point is again sent back by using the same values. Means now it will be translated by using xf comma yf, right? So that it will be like, see, you are moving this particular fixed point by same amount, so that it will come to this location. So as shown in the diagram D, your final triangle will come to the required location. Okay, so whenever you have to perform rotation of the object with reference to a fixed point, you have to perform the steps like, first take the fixed point to origin. Okay, see, if the fixed point coordinate values are xf comma yf, then translate it by minus xf comma minus yf, so that it will come to the origin. Okay, after that perform the rotation as per your requirement. Okay, so once you complete the rotation, again reverse translation that object by the factor xf comma yf. Okay, so that now the final image as shown in the diagram D here, it will be the rotated object by the given angle, right? So as we are not having direct matrix for this purpose, so we have to do these particular steps that take to the origin, then perform the rotation, and then do the reverse translation. So by after following these three steps, we are getting that the particular object, like a triangle in this case, is rotated with reference to a given angle. Okay. So see, fixed point may be anything. Sometimes the fixed point may be center of your triangle or center of your object. It may be say any vertex of your triangle or the object under consideration, right? It may be any vertex, it may be center of that particular object, or sometimes it may be randomly selected object. It may be any randomly selected pixel. Not necessary that it should be always within that particular object. Maybe possible that I want to just rotate this particular triangle with reference to this point, right? It's possible. So here, if I have to rotate with reference to this point, I have to take this to origin. So same procedure I have to follow. So after all, the fixed point or pivot point depend on the situation. Whatever fixed point is given to you, based on that you have to work. All right. Here again, how we can perform the scaling with reference to a fixed point is given. All right. Scaling with reference to fixed point means that particular fixed point will not change its location. That particular fixed point will not change its location. Okay. So here again we are considering the same kind of triangle. The triangle within this triangle, a particular fixed point except comma yf is considered. So this particular fixed point is taken to the origin. Okay. So as shown in the diagram B, we are getting that particular fixed point at the origin. Correct. And now, as shown in the diagram C, that particular object is scaled. Scaling of that particular object. Here it is actually enlargement, right? So scaling factor must be taken greater than 1. So scaling of the object is done. And after that, this particular fixed point is again translated to its original location. So the procedure almost same as we have done for rotation with reference to fixed point. Correct? The process is almost same. Correct? So as we have discussed, the fixed point may be any point. It may be center of your diagram. It may be any arbitrary point selected here. It may be vertex. So the thing depends totally on the requirement. What is requirement of your program? What is requirement of your project? So based on that, you have to select a particular fixed point. With reference to that, you have to start rotating the given object. Right? So see, about the scaling, we have seen that if you are doing scaling with reference to origin, normally scaling is nothing but we are directly doing the multiplication factor. So if I am reducing size of the object, in the previous session or prevision, we have seen that that particular object will move towards your origin. When you enlarge the object, that particular object is moving away from your origin. It happens like that. Okay, so the procedure remains almost same when you perform rotation or scaling of the given object with reference to a fixed point, right? You see here it is a point about concatenation properties. Concatenation properties means what will happen if you perform some operations one after another, something like that. If you are performing the same kind of operation one after another, then the output doesn't hamper whatever sequence you have followed. Like say, if I am taking translation, say if I am going to perform 3 translations in a sequence, say first I translated by 10, then translated by 20, then translated by 30. So I have done in sequence 10, 20 and 30. See, if I have done the change in sequence, like say I have first done 20, then 10, then 30, it doesn't matter, right? Both the outputs will same. Okay. However, you may get different kind of output when the two sequential operations may be different. For example, I have done translation and then I have done rotation. Okay, this operation I have done, and after that I have done first I have done rotation and then I have done translation. So the outputs will differ as shown in this particular diagram. In A, we have first done the translation. This is original object. I have done translation, then I have done rotation. I got the object here. Here I have done rotation and then I have done translation. So both the things are change. Okay. When same kind of operations are happening in sequence, then they will happen. They will generate the same kind of output. Okay, they will generate same kind of output. As I have given you an example of first translation by 10, translation by 20, and translation by 30. The output I will get same. Right. However, output will different when I am performing two different kind of operations. Okay, the output may change as shown in this diagram. Okay, with this I completed one part of this particular session. So next we have to start with say reflection of object and shear transformations. Okay, so note down some of these points about the reflections. Note down these points about the reflection. Reflection means what? Basically, reflection means we are trying to get mirror image of the given object. Reflection means we try to get the mirror image of the given object. Okay, in day-to-day life we see ourselves in the mirror, right? That's why you are well versed with what is meant by the mirror image. Correct. The same thing you are able to see in the mirror, right? So if I have taken a pen or if I have taken a pencil, something like this, then I will get mirror image of that particular object, right? I will get mirror image of that particular object. For example, if I have taken this particular CD, right? If I have taken this particular CD, I want to get its mirror image with reference to this horizontal plane, right? So its mirror image will be exactly at the same distance here, correct? So see whatever part, see here my thumb is near to this particular plane, right? Then it will be in the same way here, right? So that whatever is displayed like this here, so its mirror image is taken at this. So it's very basic concepts of this particular mirror image. Okay, so we are actually trying to do reflection means it's as good as performing the rotation with 180 degrees, something like this, right? So a reflection is normally done. See, in two-dimensional objects or in two-dimensional plane, what happen? We can perform the reflection with reference to, say, the x-axis, that is the horizontal axis. We can perform the reflection with reference to, say, y-axis. Similarly, reflection of the object with reference to y equal to x line. Perform reflection with reference to the origin. So, such kind of cases we are going to see in this reflection part, right? So, see this particular diagram, reflection with reference to the x-axis. This is the original image. The original image coordinate vertices are represented by 1, 2, 3. Okay, the vertices are given the name 1, 2, 3. Then at the bottom side, the reflected image is shown with 1 dash, 2 dash, and 3 dash. Okay, 1 dash, 2 dash, and 3 dash. These particular things represent the reflected triangle. Right now, see, consider this as the origin. Okay, in this particular above quadrant, you have drawn this particular triangle as the original object. Its mirror image is taken with reference to the x-axis. Right, we got 1 dash, 2 dash, and 3 dash triangle. Right, so actually what happens, see this, I will compare 2 and 2 dash. Okay, what will the x value for 2 and 2 dash? Will it same? The x value of 2 and 2 dash is same. Okay, the x value of 2 and 2 dash is same. This particular x value remains same for both of these, right? Okay, now tell me about the y values. See, for this vertex 2, say the y value, for example, say it is 10, then what will the y value for 2 dash? Y value for 2 dash will be minus 10. Okay, because it is at the negative y side. See, if I say that the above portion y value here is positive, right? This is origin. So at the bottom side, the y value will be negative. So if the y value for 2 is 10, then y value for 2 dash will be minus 10, right? It will be minus 10. So same phenomena will happen with 3 and 3 dash, right? For 3, x value will remain same, y value will become negative when it comes to 3 dash. Same way for 1 also, the x value is same. Only if its y value is say 80, for 1 dash, the y value will be minus of 80. It will be minus 80, right? So the same thing is represented with help of this matrix. So matrix for reflection with reference to x-axis is given by 1 0 0 0 minus 1 0 0 0 1, because the x value will remain same. Okay, x value will remain same and y value is negated. Correct. See, current value of y is positive. In this case, it will become negative. If the y value, current y value is negative, then it will become positive, right? So what, x value will remain same and y value is negated. So the matrix will be 1 0 0 0 minus 1 0, and for third row it is 0 0 1. Okay, so whenever we are performing reflection with reference to x-axis, x value remains same and y values are negated. Now see another case, reflection about the y-axis. We are the diagrams showing the reflection about the y-axis. See here, triangle with coordinate, the vertices 1 2 3. Okay, this triangle is given its reflection or mirror image is 1 dash, 2 dash, 3 dash. So here y value remains same, correct? The y values remain same. However, x values are changed. See here for this vertex 1, if the x value is minus 30, right? Because it is at the left hand side of the origin, so it will be say minus, right? So if this value is minus 30, then for 1 dash, the y value will be plus 30, right? If this y value here is minus 30, it will be, sorry, if the x value is minus 30 here, then the x value for this will be plus 30, right? But y values will remain same. Y values will remain same, only x values get negated. X coordinate value of these objects get negated. So how it is represented in matrix format? In matrix format, it is given in terms of minus 1 as this position representing the x value, correct? So it will be minus 1 0 0 0 1 0. This location represent the y value, right? So the y value represents same, so there is change in only the x value, right? So this is about reflection reference to the y-axis. Now we come to next point, that is reflection reference to the line y equal to x. So when we are performing reflection reference to this particular line y equal to x, this original object, it is reflected here, right? So the x and y coordinate values are just changed. So it is represented by 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay. So x and y values are just swapped. And when we are performing reflection reference to the origin, this is origin of the object. This is origin of the object. This is the original triangle. Its reflection we have taken with reference to origin. So x and y values will get negated. See here, x and y value both are positive for the original image. So when it we take reflection reference to this particular origin, x value will get negated as well as the y value get negated, right? So in this way, these reflections are handled. Now we see the next point, that is shear transformation. In shear transformation, basically the shape of the object get distorted. Shape of the object will also change. Okay. So shearing transformation, there are two kind of shearing transformation, that is shear in the x direction and shear in the y direction. Shear in x direction and shear in the y direction. So these two types of shear transformations are there. So in shear transformation, what is actually done? It's as good as we are applying some force on that particular given object, as shown in the next diagram. See here, just assume that we are applying a shear transformation in x direction. So shear transformation means nothing but when we are applying it in x direction, on the top surface, or in other way, the surface which is away from your origin. So at this particular surface, we are applying force in horizontal direction. We apply force in horizontal direction. Now just assume that I have a bundle of papers. And on this particular bundle of paper, I applied some force. From the horizontal direction. Okay. So what will happen? The topmost paper sheets from the bundle will just slide. Alright. They'll slide more, and below that there are some papers, something like that. Till the bottom, the movement will be less, right? Like this. Just imagine that in the x shear, at the location 0, 1, you have applied this horizontal force. So because of that, this upper layer will go ahead. So there will be some sort of disturbance in the lower papers in the bundle, right? So your object will look like this. Correct? The bottom level, because you are applying the force on the top. So the topmost papers in the bundle will move more as compared to the bottom papers, right? And the final bottom paper here, lowest layers, their movement is very less, right? So by applying the shear, it will be created like this. Your particular shape of this particular object will become like this. So here, as we have seen that, as the force is applied on topmost layer, right, there is too much displacement or movement in the upper direction compared to the lower portion of that particular object, right? So what actually happens, shape of that particular object is distorted. Correct? Previously it was rectangle, now the shape is totally distorted. Okay, so we get something like this. So bottom portion remains same. Okay, so shear in x direction, its matrix format is given as 1 SHX. SH indicates shear and x indicate x direction, y indicate y direction. Okay, so as we have applied it only one, that is x shear here, so it will be 1 SHX 0 0 1 0 0 0 1. Okay, so proportionate transformation will take place there, so that x dash will be equal to the previous value of x plus the shx into y. Why the multiplication with y is done? Because the upper portion is having more movement compared to the lower portion. Upper portion is having more movement compared to lower. So it depends on the y value, right? So that x dash is equal to x plus shx, that is the shear in x direction, into the y value, and y dash will remain same. Y dash is equal to y, right? This is for x shear. Now we'll see how the y shear is done. In y shear, what we do, we apply this force in vertical direction, and here we follow the same rule. Whatever vertex is away from this, the bottom vertex, correct? The bottom vertex which is away from this origin, to that particular vertex we are trying to apply this force. Okay, we applied force here. So see, rectangle which is drawn, hollow rectangle drawn with the black diagram. Okay, black portion is the original diagram, and we applied this particular force. I can call it as SHY, shear force in y direction. Okay, so after applying this force, this particular bottom point reaches to this, right? The pink diagram shows that the original object after the distortion, okay, or after applying this SHY, how that particular object will look. So this pink portion is shown, like pink portion is the particular rectangle, how it will look after applying the force in SHY. Okay, or when we are apply the force, shear force in the y direction. So matrix for this will be 1 0 0 SHY 1 0 and 0 0 1. Okay, so in this way the x shear and y shear, they actually distort, they create distortion in your original image. Shape of the image will change. Okay, after that a small point we can discuss about the raster transformations. If you see the syllabus carefully, raster transformation is not mentioned in the syllabus, but in previous all the years the raster transformation was one of the point in the syllabus. That's why I thought that I have to give you brief information about this raster transformation, because I'm sure that it will help a lot to you when you are performing your mini project in graphics. Okay, when you perform the mini project or animation kind of stuff in graphics, computer graphics, it will help you to take help of the raster transformations sometimes. Okay, raster transformation means basically what? See, you have seen all these kind of transformations like say reflections, etc., where you basically work on say vertices of the given object, right? You basically see, if I consider this particular diagram, I'll consider this vertex, this vertex, this vertex, right? And I'll perform its reflection and get the object. So we are actually performing reflection of the vertices and draw the triangle at destination. Okay, but we are not taking something like from this particular triangle, read 1 pixel here, put it here, take the second pixel from here, display here, take second pixel, put it here. Something like that we are not doing. Whatever methods we have seen earlier, like translation, rotation, scaling, shear transformation, then this particular reflections, etc., we are not doing the movement of each individual pixel, right? What you do, if there is a line, we take endpoints of the line and we perform transformation, a particular transformation of that particular line endpoints, correct? A transformation of that particular vertices indirectly for any kind of object, I can say, and we redraw the diagram. However, in raster transformation, what will be done? For example, I have to perform reflection of this. Then in raster transformation, each individual pixel will be read. Each individual pixel from this particular triangle will be read, and it will be put one by one. Okay, that's why it is called as raster. In raster transformations, we work on each individual pixel. We read one pixel, display it there, read another, keep it there. That particular process we go on doing till all the pixels from that particular object are over. Okay, so coming to the required slide. For example, we have to perform raster transformation, means taking the image upside down. For example, this is a particular object and we have to draw this particular object upside down. For simplicity, we assume that this particular diagram or particular object having black boundary and it is filled with the white color. So as the arrow shows, see this is the original object. As the arrow shows, we start reading from this. Okay, I read this particular vertex. When I'm displaying it, this arrow shows that I am displaying from this direction. So this particular thing I have taken, I have put it here. I have read this second point, read here, put here, the third, put next, something like that. So this particular point will read first and this particular point will read last, right? So it will be displayed like this. So you are reading one pixel at a time and go on putting there. Read right, read display, something like that. And here for every pixel, see as this is a pure case of translation, right? So when I read one pixel, I have to apply translation on that and then display the final output, right? So in this way, when I'm doing, I have to do upside down the particular image. I will start from this upper portion here. I will read this, and when I am putting it here, as I have to make it upside down, I will read here, and while I will putting, I will put from this. So when I take the next line, it will put here. If I have to display same thing here, then what I'll do? I'll read from here, display it here. Read from here, display here. Something like that. Sorry. Same way, raster transformation for rotation can be done. The green object is showing that the original image, and this with purple showing the thing after rotation. How we can perform the rotation? It is case of 90-degree rotation with some translation also, right? So here see what is done. I have read this particular pixel, it is displayed here. Okay, read the next pixel from next line, it is displayed here. Like this, when I read this pixel, it will display here. Read this pixel, display here, something like this. So in this way, we do it in horizontal way. We have rotated that particular object. Okay, we have rotated this object given in a green diagram or displayed in green color. It is rotated in the other way. For simplicity to represent, I have given different colors. Okay, I have given the different colors so that green is considered as original image and the purple color image is the destination image. So in this way, it's possible for us to rotate these particular objects. Okay. So in this way, the raster transformations can be done. Yeah. See, if someone asks you that do scaling of the object by factor 2, say just take sx equal to 2 and sy equal to 1, means scaling factor 2 in x direction and scaling factor 1 in y direction. How you will do it? It will be very simple. I have to do scaling 2 times in x direction. What I'll do, I'll read 1 pixel from that given object and put 2 pixels. Okay, whenever I next come to the original diagram, read the pixel, I will display it 2 times. Okay, so I'll read 1 pixel, display 2 pixels. Read 1 pixel, display 2 pixels in horizontal direction, right? So automatically, if I read 100 pixels from the original diagram, my destination diagram is having 200 pixels in horizontal direction, correct? We are not doing it for vertical direction also, correct? So when I put only Sx equal to 2, then for the original image there are 100 pixels in X direction. Now I got 200 pixels in X direction. Okay. See, if someone asks you to perform 2D transformation of your object, 2D object is given to you, and you have to perform, say, uniform scaling with Sx equal to 2 and Sy equal to 2. How it can be done by using raster transformation? You have to do it by when you read 1 pixel from that particular original image, you have to display 4 pixels at the destination. The reason is that scaling factor is 2 in X. In Y is also scaling factor 2 is there in X direction, also 2 in the Y direction. So 2 into 2 is 4. So you have to display 4 pixels. When I read 1 pixel, read display 4 pixels. Read next pixel, display 4 pixels. So in this way you can do it so that the object will be scaled uniformly in X direction as well as in Y direction with Sx equal to 2 and Sy equal to 2. Okay. So with this, we concluded the, say, revision part of the 2D transformations. Okay. So go through it. Thank you.